today, if you didn't already believe it, you've already seen half a day of talks kind of showing you the power of these methods. The downside is tuning these systems, getting the right configuration parameters for them, is extremely non-intuitive. This is often like brushed under the rug when you're talking about deep learning and machine learning, but there's still a lot of these kind of magic numbers that make the systems work. Things like the number of hidden layers in a neural network, or even the number of trees in a random forest. In fact, Xavier here, who's also a former MLconf speaker, recently had a Quora interview where he talked about this is one of the hardest and most unsolved problems in machine learning today. Understanding how these complex systems work and being able to describe the underpinnings of them, as well as having a more or less automatic way to tune them. So that's what Bayesian global optimization represents, is a more or less automatic way to tune these systems. And the reality is every single machine learning pipeline, framework, and method has these tunable parameters. Once again, it could be as simple as the number of trees in a random forest, the regularization parameter in logistic regression, or all of the different knobs and levers that you get in a deep learning system. This might be familiar to some of you. This is a really fun website, playground.tensorflow.org. Lets you train a neural network in your browser. So what we're trying to do here is 2D binary classification. We have orange dots, we have blue dots. We want to learn a surface that differentiates them. So imagine you're doing fraud detection. You can know everything in the world about the context of your underlying problem and the data set itself. You phrase it in such a way, then you feed it over into TensorFlow to come up with some model that's able to do this classification for you. The problem is there's 22 different knobs and levers here for you to tune and tweak in order to get that model to be as performant as possible. Once again, this is completely orthogonal from the domain expertise you applied to gather the data, do the feature engineering, do the machine learning engineering to actually get the model up and running, understand the output, etc. This is literally just black box, trial and error based optimization most of the time. But more often than not, you're not playing with graphical interfaces. It's actually much worse than this. As you start to look into the open source, this is the RMS prop stochastic gradient descent optimizer with an MXNet, you start to see lots of little magic numbers creep up. So here we have things like the learning rate is 0.01, gamma 1's 0.9, gamma 2's 0.9. Where do these numbers come from? How do they affect what I actually care about at the end of the day, which is maybe the accuracy of that fraud detection algorithm that we're building? Worse, the intuition here is not only very difficult to gather, but it's often very time-consuming and expensive as well. Every single time you want to spin up a cluster and do deep learning, it may take many hours or potentially days to get the response, and sometimes the documentation is less than obvious. Here we have a decay factor for moving average for gradient squared. Should that be higher or lower if I'm dealing with image data? Very difficult to come up with. So often this can feel like you're trying to climb a mountain in the fog. And the analogy here is, it's very time consuming and expensive every single time you try a different deep learning configuration. But if I told you to find me the highest possible altitude on this mountain, and all I gave you was a latitude and longitude, it would also be very expensive to get there. But as a human, you might think of different clever ways to go about solving this system. And in fact, there's many common ways that people tell you how to attack this in practice. So let's say we have some machine learning system that we want to be able to tune. We've already gone through all the time-consuming effort of doing feature engineering, understanding the domain, the context, etc., built up some way to do validation so we can actually trust whether or not we're getting good results out of this pipeline or not. And then we need to set all these configuration parameters. Hopefully you're setting these. More often than not, the actual default hyperparameters are hand-tuned to make the examples very performant and look good, but are almost surely not the peak configurations to get you the best performance in your data set. So if you type in scikit-learn hyperparameter optimization, then you're going to get a couple of different solutions here. One that's very popular is grid search. This is like trying to climb that mountain by going to every single possible lat long and measuring the altitude, and then at the very end, deciding what was the highest point. This in 2 dimensions already sounds crazy, but it grows exponentially with the number of dimensions you're tuning. So back to that neural network example, if we have 20 different knobs and levers, the exponential to the 20th power becomes extremely large, even if it was relatively cheap to evaluate the underlying system, which more often than not, it isn't. So to combat this, it's become really popular in the literature to do things like random search. James Berkstra has a great paper from 2009 saying in practice, this actually outperforms the grid search quite frequently. The problem here is this is like trying to climb that mountain by jumping out of an airplane and hoping you land at the peak. Once again, not intuitively the best way to go about doing optimization, although in practice it can be a little less time consuming than something like grid search. So sometimes when you go and you talk to people about setting up these systems, they say, well, just build intuition about it. Just try different things and try to learn how it works. Once again, in practice, humans are pretty bad at doing 15, 20-dimensional optimization in their head. And more often than not, any intuition you build on one system doesn't necessarily apply to a different data set, different architecture, or whatever it may be. This can also be a huge drain on that domain expertise and contextual information that could actually provide huge gains to the system, like doing better feature engineering and understanding the objective metric that you're actually shooting for. So there's a handful of different ways that you can attack this problem beyond this. There's different kind of convex optimization strategies. You can do things like gradient descent, although once again, that becomes extremely expensive in this derivative-free context where you can only sample a single configuration that might have categorical, integer, or continuous parameters, and then you need to be able to decide what to do next. Even approximating a gradient can be very expensive in high dimensions. There's other global optimizers like simulated annealing, particle swarm, genetic algorithms, but these often make the assumption that it's very cheap to evaluate that underlying fitness function. So what we need is an optimization strategy that treats every sample as precious and guides us to the best configuration as efficiently as possible in terms of the number of evaluations required. So Bayesian optimization to the rescue. Once again, there's a lot of different open source techniques for doing this. I wrote Mo at Yelp. One of our other research engineers wrote BayesOpt, Spearmint, HyperOpt. There's lots of different popular strategies out there. You can think of SigOpt as an ensemble of all of these different techniques, but I'm going to be using that interchangeably with Bayesian optimization in general, and you can think of them as roughly the same. So what we want to be able to do is have a system that can suggest configurations that you then perform within your system. You observe some output of how that configuration is performed, and then we want to learn from that to decide what to do next, and repeat this process in order to guide you to the best configuration in trying as few as possible. And it's worth noting that all of these algorithms are black box in the sense that they can only observe the inputs and the outputs of the system. They don't get any sort of introspection or information about what's going on underneath the hood, which is really great because that means it can be applied just as readily to tuning a support vector machine or a gradient boosted tree as it is to doing a deep learning system. The downside here is a black box optimizer will optimize towards any metric you give it. And that can be extremely painful if you're optimizing towards a metric that's going to tend towards overfitting or something like this. So this requires you to do a lot of applying of your domain expertise and contextual knowledge to be able to come up with the right bullseye to aim the system at, because it'll hit it, and you want to make sure you're shooting at the right thing. That being said, assuming we can trust the metrics that we have in place, this can be a very efficient way to do optimization. So, how does it actually work? What's going on underneath the hood? So I'm going to define optimal learning, which is what operations research calls this field, in a variety of different ways here. This is my academic family tree, my PhD advisor and his PhD advisor. So we have some time-consuming and expensive system that we want to efficiently sample. When I was at Yelp, we were tuning the advertising system, so it's a huge opportunity cost every time you want to try a different configuration. But if you can do it just right, a bunch of money comes out the other end. So you can think of this as, how do I take a system that's already in place and make as much money or get as much relevance or accuracy as quickly as possible? Slightly more technically, we have some objective function that we care about. In machine learning, this is often something like loss, accuracy, likelihood. It can be an AUC or an F-score metric. It could be a combination of different things that we care about. Once again, this is what your domain expertise leads you to believe is the metric that if it goes up, you've made a better model. And then there's things that we can tune about the underlying system. Could be hyperparameters, could be architecture parameters in a neural network, could be feature transformations, could be tuning some unsupervised learning algorithm to learn a representation of the data before you even feed it into something else. Basically, these are all the knobs and levers that you have to set before you even go about doing the actual learning itself. And then once again, our goal is to try as few of those as possible, but still get you to the most performant version of this system. So often in the literature, these methods are classified under the umbrella of sequential model-based optimization. So it's sequential in the sense that we're leveraging historical information to decide what to do next. This is where it differs from something like a grid search or a random search, which will just blindly march along and not take into account any historical information. So we're learning from what we've done so far, and we're taking that and we're building different surrogate models. This is the model-based component of it. So we want to be able to say, given what we've sampled so far, what can we expect from sampling things nearby? How much can I learn from what I already know to see what's going to happen somewhere where I have no actual information? And then the optimization component of it is take those surrogate models, do something intelligent with them to decide what to sample next, and repeat the process. So once again, there's many different ways to do this. A very popular one, which I'll go into here in a minute, is Gaussian process-based, but you can also use tree of Parson estimators. You can even use a Bayesian neural network to tune the underlying neural networks. It can be turtles all the way down. But I'm going to walk through a very specific framework so that you guys can get some intuition about how these black box optimizers actually work. So this is going to be using a Gaussian process as that surrogate model. It's going to be using expected improvement as the actual optimization criteria. And then it's going to be sequential in the sense that it's going to learn as it goes. So I'm going to walk through what each one of these means in a minute here. But once again, you can use almost any sort of framework to do this. Other popular ones include using tree of Parson estimators or Bayesian neural networks. This is the underpinnings of both the metric optimization engine, which I wrote, and Spearmint, which came out of Harvard a few years ago. First up, what's a Gaussian process? So I'm going to try to teach you guys basically a graduate course here in 5 minutes with no questions. So if you have any questions, I'm happy to answer them at the booth right next to the books, or there's some great books online that go through this as well. So once again, the goal here is to come up with some sort of surrogate function for the response of this objective that we're trying to maximize. So let's say we can tune something like a learning rate. That's the x-axis here. And we're trying to intuit what the response is by trying different learning rates. So we can do that with what's called a Gaussian process and explicitly model every single potential response from each possible learning rate as its own independent Gaussian. What that means is, as we start to sample points, we can say, with this stochastic regression method, I think I'm going to observe a response near what I've already observed before. So at the beginning, we had no information, but as we start to sample points, we can update the posterior of our Gaussian process and say, given that I've already observed this objective response at this learning rate, I now have a better idea of what I can expect to see when I try different learning rates near there. On top of that, how this differs from kind of a traditional regression method is it gives us this notion of uncertainty. In regions where we have very little information, there's high variance in the actual output. And so we can use that to decide whether we're exploring more, learning more about the underlying system, or exploiting that information to drive us to a local optima. So you can just think of this as a very flexible stochastic regression method that can take in a sparse amount of data, but build up this easy to manipulate system for you to understand what you think is going to happen. There's another way to think about Gaussian processes if the point-wise perspective doesn't suit your intuition. So once again, in the point-wise perspective, every single potential configuration is represented by some Gaussian with an expected response and some variance. The other way to think about Gaussian processes is from the functional perspective. So At the end of the day, what we're trying to do is model some system. And when we have no information, any function in the universe could represent the response of that system. So let's assume we have a bag, and in that bag is every function in the universe. As we start to sample points, we can start to throw away functions that don't make sense anymore. If we've sampled a point with no noise, then any function that doesn't pass through that point can no longer be the response of our system. And so we throw it away. What we're doing here is building a functional distribution, and that's what the Gaussian process is. There's some most likely function, which is the mean of the Gaussian process, this black line here, but there's these dashed lines too that could represent the underlying response. So it's either an infinite number of Gaussians in the parameter space or an infinite number of functions in the response space. Gaussian processes themselves have their own tunable parameters. So what's underneath the hood here is this notion of a covariance. If I sample a point A, how much information does that give me about another point B? And how does that information vary over different length scales and dimensions? And we can basically take information about what we've already sampled in order to find the most likely kernel and the most likely parameters for it, in order to say, given what I've observed, this is the most likely Gaussian process to represent my underlying data. Because at the end of the day, like any regression function, if you're not careful, you can overfit or you can underfit. But at the end of the day, you want to be able to come up with some good representation. So this is handled kind of automatically by some of these optimizers. So that's how Gaussian processes work, but once again, we were only using that as a stepping stone. We're not actually trying to model the response of these individual configurations. We just want to get to the best configuration. So what we're going to do is we're going to take that underlying surrogate function and just use it in order to decide what to sample next. So we can apply different acquisition functions to it. So expected improvement is a very popular one in the literature. What this is trying to do is say, find me how much I expect to beat the best thing I've seen so far by. So we're playing King of the Hill. We have some great point, and we want to say, in expectation, how much do I think this new configuration is going to beat that best point? So what you're looking for intuitively is points that have a reasonably high mean, a high expected response in your surrogate function, but also enough uncertainty that you think you can exploit that to get some cool new information. You want to try to get lucky. This expected improvement is a great acquisition function in trading off both exploration, learning about that underlying system, and exploitation, leveraging that to resolve local optima. So what we have here is the expected improvement plotted for this Gaussian process. You see it wants to sample this point on the right. We do so. That updates the posterior of our Gaussian process. We have this new representation of the world. That changes where we expect to see improvement. We no longer expect to see any improvement on that right side because it performed relatively poorly. And this is once again how it differs from some of these more naive methods that could just blindly sample there again, or in lockstep of a grid, just continue sampling in this bad region. Now we want to sample on the stage right, your left. So we sample there. Once again, updates the posterior, updates the expected improvement. At the beginning, it's doing mostly exploration. So once again, it wants to learn as much as it can. It wants to figure out how these parameters interact, over what length scales, how they combine to affect this objective we care about. But then it will very rapidly switch into exploitation mode, resolving this local optima, and then explore again. Because once again, there's no utility in over-optimizing some convex optima, because if you already know what the result is, you don't expect to improve upon it. So it'll go back out and continue to explore and exploit. And it creates this very nice global optimization strategy that's able to perform this task relatively rapidly. So I'm running out of time here, so I have like 3 or 4 more minutes. Once again, any questions can be addressed at the booth, but I'm going to dive through at least one example here so that you guys can see what this looks like in practice. So this was some joint work that we recently did with AWS, and it was on their AI blog about 2 weeks ago. What we did is we took one of the examples from MXNet on doing classification using a natural language processing system to do sentiment analysis on Rotten Tomato reviews. So what that means is we look at Rotten Tomato reviews and we want to say whether or not that person was positive or negative. It's kind of a classic NLP problem. Turns out you can use convolutional neural networks to do this very well, but these convolutional neural networks have a lot of tunable parameters. So we took the example and we bolted this Bayesian optimization system on top of it in order to tune its hyperparameters and feature transformation parameters with the goal of increasing accuracy. Once again, things like MXNet have lots of tunable parameters deep underneath the hood. In addition to that, they can actually have a pretty large effect on how you actually get the weights of these underlying neural networks. Things like the stochastic gradient descent optimizers themselves. Different tunable parameters can result in very slow convergence or very brittle convergence, or sometimes it'll just bounce around the actual optimal weights. Additionally, there's different feature transformations you can apply to this, different architecture decisions you have to make. Basically, lots of tunable parameters throughout. All this code's on GitHub, and there's a much more detailed post on AWS's AI blog. So we wanted to basically say, given the standard approaches to this, which one can get me to the best results as quickly as possible? Grid search, random search, or this ensemble of Bayesian optimization techniques. And what we were able to see is across the board, for basic systems where we're only tuning kind of continuous parameters of MXNet, and systems where we're also tuning architecture parameters, the Bayesian methods are able to get to better results 10 to many times faster than the standard methods. And this extends to any sort of like fixed budget and across multiple independent optimizations as well. So the moral of the story here is, if you're doing parameter optimization, if you're dealing with these complex, sophisticated machine learning frameworks, don't try to do the 10-dimensional optimization in your head. Don't try to brute force it. You can do better than random. There's lots of great open source out there, or SigOpt's there to help. So thank you very much. Yeah, I don't see Courtney yet, so I'll start answering questions. Yeah. Yeah, great question. So do you see different results based off of what you're actually trying to optimize? Is that the question? Yeah, and we definitely see that. There's certain methods that actually work reasonably well in a lot of different contexts, like a random forest is kind of designed to give you a B+ answer, kind of almost whatever you tune the hyperparameters. Neural networks tend to have a much higher variance in the response, depending on the different hyperparameter configurations you have. Something simple like just tuning the iris data set with an SVM, like there's only a few different options you can actually get, so it's a relatively boring space. We have an ICML paper that we presented last year that goes into how we go about building up a robust evaluation framework to make sure we perform well in a wide variety of contexts, and that's on our website. I'd be happy to pass that on. But in general, you do see very different kind of results depending on what you're optimizing. Yeah. Yeah, great question. So it was like, the question was, do you optimize for a specific data set in a specific model, and do you need to look at the underlying data? Once again, this is entirely black box optimization. So all we see are the inputs, which are the different configurations, and the output, how well it's performed. So the underlying data set could be whatever it is underneath the hood. The model could be whatever it is. When that data changes, you might want to go back and re-optimize. We work with a lot of different algorithmic trading firms that do this daily because the data changes so much day to day. But in practice, the methods are agnostic to what's happening underneath. Yeah. Yeah, the question was, it can be used across a wide variety of models. How do you reuse it? You would just restart the optimization. So if you were tuning a support vector machine, and then you were also tuning a random forest, you would just treat those as independent optimizations. And it would learn the different response surfaces for the different types of parameters. Yeah. Do I have time for one more? All right. Yeah, so once again, the question was, can you use this for ensembles? Once again, it's agnostic to what's happening underneath the hood. All it looks for is what are the continuous integer and categorical parameters that can be tuned. So that could be a simple model, it could be an ensemble of models, it could be a pipeline of models, whatever it is underneath, as long as there's tunable parameters that come in and some way for you to observe the output that comes out. Any further questions, I'd be happy to take at our booth. We'll be here for the rest of the day. Thanks again so much, everyone.